Hello everyone, welcome to my presentation. My name is Yuxuan Wen and my advisor is Professor Ida Zhang. We are from University of Colorado at Boulder. Today my topic is evidence of a unique critical fabric surface for granular soils. In soil mechanics, the internal structure of the soil has a huge influence on the soil behavior, and there are many methods to describe the internal structure of the soil. The most common way is to use a second-order fabric tensor to describe it. This fabric tensor can be void-based or contact-based, and the contact-based fabric tensor is most commonly used in the field. For example, the first figure is a granular packing in the DEM simulation. To describe the internal structure of it, we look into the contact network of this packing, as shown in this figure. Then we can quantify the internal structure by calculating the fabric tensor EIJ from this equation. In this equation, n is the contact vector, rho n is the contact direction distribution function. The main part of the fabric tensor is delta, also known as the coordination number, and the deviatoric part is F, also known as the fabric anisotropy. With the fabric tensor defined, many studies found that the coordination number and fabric anisotropy has a unique surface or relation at a critical state. For example, Zhao and Guo in 2013 identified a unique critical state surface on the fabric pi plane, shown as the red circle. Then Kruid and Rothenberg in 2014 found a linear relation between the fabric anisotropy and coordination number. This result inspired us that there may be a unique critical fabric surface in the principal fabric space. So in 2020, we drew a sketch of this surface and proposed a constitutive framework based on this surface. In this sketch, the hydrostatic length is proportional to the coordination number, and the distance from a point on the surface to the hydrostatic line is proportional to the fabric anisotropy. If we cut it along the hydrostatic line, the relation between the coordination number and the fabric anisotropy is obtained. If we cut it perpendicular to the hydrostatic line, the fabric space on the pi plane is obtained. Now, someone may question that the shape of the surface in Fig 1 is reciprocal to that in the sketch figure, and the fabric anisotropy in Fig 2 decays with the increase of coordination number, which is also different to the sketch figure. This is because that our fabric anisotropy F is not normalized, or their fabric anisotropy is normalized by the coordination number. Again, this is just a sketch figure. What is the real shape of the critical fabric surface? Does it exist? How does it look like? So, to answer these questions, we conducted a series of triaxial tests. The loading part of them are presented. The first one is the isotropically consolidated true triaxial joint test, also referred as the CID test. All this test is shared on the different intermediate principal stress ratio, B value. And the second test is the true triaxial on-joint test, referred as the CIU test. And they are shared on the different intermediate principal strain ratio, BE values. These two tests are conducted on the medium dense specimen. Apart from the medium dense specimen, we also performed triaxial joint test on loose and dense specimens. And the last test is anisotropically consolidated triaxial joint test. This test is also adopted to verify the uniqueness of the critical fabric surface if the specimen has some initial fabric anisotropy. A typical result for joint triaxial test are presented. So in this case, we only show an example of compression test for briefness. It is obvious that all the specimens under different confining pressures evolves to the same critical state stress ratio, and the normalized fabric anisotropy at the critical state decays with the increase of mean effective stress. For the critical state fabric data, it shows there is a surface in the principal fabric space. The left figure is total contact fabric space, and the right figure is strong contact fabric space. Here, we define that the strong contact is if a contact force is larger than the average contact force of all the contact network. then this contact is a strong contact. The critical fabric surface on the fabric pi plane can be mathematically described by this equation. But however, this surface only contains the fabric data that is in the high coordination number regime. In the low coordination number regime, there is an absence of that fabric data, and we don't know whether there is a surface in this low coordination number regime. So this is why we need the unjoint triaxial test data, because the unjoint triaxial test can be liquefied, and the coordination number will be very small since the mean effective stress is close to 0. So this is an example of unjoint triaxial test result. Several specimens under small initial confining pressures are liquefied, and the other tests reach to the critical state. The result is as usual and obvious. This is the fabric evolution of unjoint compression test. The x-axis is the coordination number, and the y-axis is the fabric anisotropy. Since all the specimens are isotropically consolidated, so all of them start from a low F value, and their coordination number increases with the increase of confining pressure. When loading starts, the fabric anisotropy all increases, but these 4 specimens with low initial confining pressures liquefied, and upon liquefaction, the F and coordination number delta all suddenly drops to 0. Then, as loading continues, the fabric path of these 4 specimens all evolves on a unit curve. For other non-liquefied tests, they reach the fabric anisotropy goes to the peak value and then drops to the critical state value. Similar observation is also found in the strong contact fabric space. Then we combine the result of joint and unjoint test. Only the compression test results are presented. It is shown that there is a threshold coordination number, delta T. Below this value, there's a unique critical fabric path for liquefied specimens. Above this threshold, the data are the critical fabric of non-liquefied specimens, and we can use a single curve to capture the critical fabric data for both liquefied and non-liquefied specimens. For the strong contact fabric, the result looks similar. The difference is the best fit curve equation is different. Now the critical fabric surface can be expressed as follows. There are 3 variables. The first is the coordination number, and the second is the parameter C, which determines the shape of the surface of the fabric pi plane, and its value is exactly the ratio of fabric anisotropy at extension to that at compression. And the third variable is the load angle. Since the equation is known and F delta, C delta relation are all calibrated, the critical fabric surface can be drawn, but we still want to validate this surface by other triaxial tests with some different initial weight ratios and with some initial fabric anisotropy. So the critical fabric surface is plotted with other test results, such as joint triaxial test conducted on loose and dense specimens, and joint triaxial test conducted on specimens with initial fabric anisotropy, and unjoint triaxial test with intermediate principal strain ratios other than 0 and 1. In this figure, it shows that all these data are on the critical fabric surface. And we also quantitatively evaluate the error by comparing the real F data to the F projected on the surface. We can see that all the data locate or are close to the 1-to-1 line, and the R² value is close to 1, which means the error is small. So the uniqueness of the critical fabric surface is validated. So now we have the conclusion. The first is a granular assembly has a unique critical fabric surface that is independent of the shearing mode, the initial state of the specimen, and the drainage condition. In this case, our fabric tensor definition is contact-based fabric tensor and is non-normalized. And the second conclusion is fabric states maintain some geometrical relations, even if the soil is apparently liquefied. Now we obtain a unique critical fabric surface. But how do we use this surface? What is the potential application of this surface? In our 2020 paper, we proposed a critical fabric theory that considered the soil fabric as the single critical state variable, while all other variables, such as the void ratio, the mean effective stress, the deviatoric stress Q, these variables attain the critical states as a result of the fabric tensor reaching the critical fabric surface. By the fabric porosity relation, the critical fabric surface can be projected to the classical critical state lines. By the fabric stress relation, we can get the yield stress and bonding surface in the stress space. By the fabric evolution law, we obtain the flow rules. So whether the soil fabric tensor reaching the critical fabric surface is the only criteria to determine if soil reached the critical state. This theory provides a basic platform to interpret the various stress-strain fabric relations. And our critical fabric surface paper now is under the second round review in geotechnique. Thank you for your attention. Any questions?